Hi, Paul Beckwith, and today's topic is methane in the Arctic. Methane, if your house is running natural gas appliances like a stove or something, or you're heating your house by natural gas, well, natural gas is over 90% methane. There's some CO2 in it. They throw in hydrogen sulfide so it stinks, so that if there's a leak you can smell it and bail out of your house before it detonates. Basically people fart, and that's mostly methane, right? Methane comes from bacterial decomposition of organic material in the absence of oxygen. If oxygen is available, it forms CO2. If oxygen is not available, it forms methane. So inside your body, in your digestive system, it's the methane. In cows, it's coming out of both ends because of the design of their stomach. Okay, there's actually, here's an idea, let's cut back methane emissions, make everybody have carbon filters on the back side of their pants or in the fabric of chairs, that would also get rid of the smell. So there you go, you get a double advantage, right? Don't laugh, there's actually some fabric materials, there's some companies I think that are starting to produce some of this stuff. So it'll increase the weight of your clothes though, right? Because it doesn't, conservation of mass. But anyway, on that thought, the Arctic concentrations in the atmosphere are much higher in the Arctic. Excuse me. Okay, I don't want to run over. I forgot to set my stopwatch, so that's okay. I'll try to figure it out. So, albedo flipping. When we lose sea ice, okay, then the ocean's darker. So the present forcing is 0.1 watts per square meter, averaged over the entire planet. If the sea ice is gone for 1 month, that jumps 3 times. And it jumps 7 times over this when there's no sea ice. Eventual disappearance year-round. So this is equivalent to a huge warming pressure on the Earth. The rate of warming in the Arctic is now a degree Celsius to 2 degrees Celsius at the high end per decade. If you take 1 degree Celsius, divide by 0.15, the global rate, then you get about 6 times. The higher Arctic is even faster. This rate will increase with the ice vanishing from the feedback, the albedo feedback. Methane sources, there's beaucoup de methane sources in the Arctic. This is from Semilitov, the Russian dudes. CH4 hydrates shown in blue, lots of them around. Terrestrial permafrost, 1,700 gigatons. Eastern Siberian Arctic shelf, permafrost, 1750 gigatons. This is on the seafloor, shallow water. 50 gigatons in precarious state, liable to sudden release. If this was released, it would cause a surge in atmospheric methane levels by 11 times, because there's about 5 gigatons in the air right now. Catastrophic feedback loops, warming spiraling up, world food production spiraling down, because weather patterns completely change and it's difficult to grow food where we presently grow it. We have to start growing it in other regions. Release of only 15 gigatons over 10 years would dominate CO2 forcing. No chance at 2 degree stabilization. I said in 2016 in February 1.8, 1.44 for 2016. Here's methane measured in Hawaii. Hawaii's a good place to measure stuff because it's sitting in the middle of the ocean. It's not near any sources, heavy industry, anything. So we measure stuff on mountain in Hawaii, and that's sort of the standard, the golden standard, if you like. So you can see methane upticking in 2007, as I mentioned before. It's rapidly rising since 2007. Human sources include fracking, leakage, livestock, both ends, as I said, industrial processes, and flaring. Okay, if we're flaring, we're actually burning the methane coming up, converting it to CO2. If we just let it come out of the stack, it comes out as methane. you know, and these stacks are out in the middle of nowhere where the oil is being refined, but there's no way, there's no piping system, there's no storage system to bring the methane to cities and stuff to be used as in natural gas. So they just either let it go up into the atmosphere or they burn it, flare it off. I think it's better if they flare it because, you know, methane is much more powerful than CO2. Natural sources, wetland. If it's getting wetter, there's more wetlands. Permafrost, thawing, and hydrates. The main sink, this is important. Methane is removed from the atmosphere by the hydroxyl ion. This is OH minus. Take water, take a hydrogen, pull it off, throw it away. You're left with OH minus, very reactive, doesn't like to be in that state. Reacts, hits methane, breaks it into CO2 and water. So the lifetime of methane on average is about 12 years, but it varies enormously. It's much longer in the Arctic where it's very dry. It's much warmer, larger in dry areas, much shorter near the equator in wet areas. Of course, it's moving, there's circulation in the atmosphere, there's mixing, but the sources are in the, you know, the sources are mostly in the Arctic because the methane level is much higher in the Arctic than anywhere else on the planet. The GWP, global warming potential, 34 times, 86 times, and 150 times, average over 100 years, 20 years, and a few years. This is relative. This is a warming from methane on a mass basis relative to CO2, which has a GWP set to be unity, set to be 1. Okay, so methane is powerful. Methane in the Arctic. Up to now, the emissions are quite small, 10 to 20 megatons of carbon. But there's been emission escalation in the last number of years, say since 2010, from both thawing tundra on land and seafloor sediments. So here's a methane clathrate, pockmarked because water is melting parts and it's creating these craters. This is methane clathrate or hydrate. The methane molecule is in the middle. Frozen water is around the edge. Now it exists in a state at high pressure, low temperature. As the temperature rises, the water cage can melt, and then the methane molecule is released. If you have a certain volume like this and convert the methane in there, the gas will occupy a volume 160 times larger than this size. This is why if this is under the ground and we get this gas produced, there's high pressure and it's creating Siberian blowholes. There was a couple of recent papers showing the craters throughout the Arctic from methane eruptions since the end of the last ice age. And also there's these huge structures, you know, 0.5 kilometer in diameter where the seafloor has been elevated up, and they're in slightly deeper regions in the craters. So, you know, we're likely to see some of these become erupting and becoming craters, sending methane up into the atmosphere. So watch the Eastern Siberian Arctic Shelf, ESAS, hundreds of plumes, tens of meters in diameter. A few years ago, that changed to hundreds of plumes as large as 1 kilometer in diameter in this Russian study area. Now, the difference in methane, just take the ratio. 1 kilometer divided by 20 meters, you're looking at area, so it's squared, 2,500 times larger. More methane. Okay, so the risk is methane starts coming up big time, clathrate gun call it, and we're rocketing up in temperature, and there's not a bloody thing we could do about it really once it starts happening. Okay, actually that's not quite true. You know, three-legged bar stool. But anyway, I'll talk about that later. Okay, Barrow, Alaska, Svalbard, Norway. Methane levels, we're seeing these spikes, these whispers, if you like, of methane coming up. You know, sometimes the data is hard to get now because these things are taken out as being anomalies. So here's the methane stores, the methane hydrate under high pressure, low temperature, and then as the permafrost, as the ocean is heating up, the sediments are warming, the methane clathrate, the water cage the ice cage is melting, the methane is released, the pressure builds up, blows holes, and comes up. If the water's shallow, it'll come right up through the water column into the atmosphere. So these permafrost and ocean floor sediments are a huge wild card, becoming less of a wild card and becoming more of a certainty as we, go to a completely ice-free Arctic. We're going to get methane coming up big time. Here's a distribution of atmospheric methane. Okay, so it's a 3D plot. We've got 2005 to 2014 here, and you can see an increase. And then this is with latitude. This is Antarctica. This is the Arctic. So as you go up to the Arctic, there's more and more methane, higher and higher levels. This is indicating that the Arctic region is the big source of methane. This is the permafrost extent, just in Canada, for example. We have continuous permafrost, the ground's completely frozen. Then you have discontinuous of some thawed regions, some frozen regions, sporadic, isolated patches. And so you can see, the boreal forest, you can see that basically, it extends fairly far south, but we're seeing, if you do bores and measure temperatures, we're seeing temperatures rise, of course, and there's huge, huge risk. We need to monitor methane more globally to find the sources and to see how much is coming from the thawing permafrost. So what does all this mean? Well, we get a disruption of the jet streams. So this is a typical jet stream. This is a low pressure area. This is a high pressure area, is the brown. The purple is a low pressure area. Between them is the white area, which is roughly where the jet streams are. This is a typical, in the past, compact configuration in a stable climate system. Now we're unstable. And we get all these waves. We get these ridges going far north. We get these troughs going far south. They get stuck. And we get completely different weather patterns. What we've had in North America is a purple over the east and west coast of North America, and brown in the middle. So really hot in the central areas, cold and rainy in the extremes. Okay, so this is downward looking on the Arctic. You can see a huge difference, and we're getting a lot more of these patterns now. We're getting a lot of the cold air in the Arctic going south, a lot of the warm air from more southern regions going north. Okay, so jet stream disruption. Here's a side view, wavy jet stream. Jennifer Francis is the 2013 paper that she wrote was all talking about this. It was controversial at the time. I mean, it makes perfect sense. You warm the Arctic like crazy. The jet streams are formed because of the temperature difference. Temperature difference to the equator drops. Jet streams become wavier, slower, get stuck. It all makes sense now. So that's a bad news for all of the, for Putin and, for people thinking, oh, okay, the Arctic's going to open up. Great, we can sail ships through. We can have cruise boats go through. We can extract, we increase the global supply of fossil fuels by 25%. We mine the Arctic minerals and just exploit it like the rest of the planet, right? Well, the problem is you can do that, but the jet streams get screwed up around the planet, and you lose all your infrastructure at lower latitudes. So this is not such a good deal in the end. So we had $6 billion of flooding in Calgary in June 2013. Well, the jet stream was twisted here. Look kind of obscene here, right? And basically in the low area, all of this rain and on snow, plug of water moves south, comes right out here. This is getting really obscene. But anyway, it peed on Calgary basically and flooded out Calgary. So yeah, this is serious stuff, folks.